Okay, everybody, welcome, CS109 on this lovely, nice day. Today we're going to talk about support vector machines, one of the most popular classifiers out there, and how to properly evaluate the performance of your classifier. So those are the big two topics that I want to cover today. But first, a few announcements. So I actually didn't try this guy. Works. So homework 1 grades went out yesterday. If you haven't received an email with your grade, please get in touch as soon as possible. So write to staff@cs109.org because you really should have received your grade by now. Awesome work, everybody. So the grade distribution looks really cool. 2/3 got an 8 or higher. So we're really happy about that. Also, just if you look at our grading syllabus, 8 is actually a good solution, just to communicate the grading scheme. Homework 2 is due already this Thursday, so I hope you all got started already. I know some finished already 3 days after it came out, but that doesn't mean you should try and outperform them and do everything in one day, right? Get cracking. Just one advice point. We ask you to please submit an executed form of your notebook. That does not mean that the TFs don't run it at all, but it makes it much easier for grading. The output is already there, and you can get an impression of the work before you have to execute all the cells yourself. But some people with homework 1 went overboard with that and actually submitted all their print test outs. Right? Like if you scrape a lot and you just want to print that for yourself to get an impression, by all means do that, right? This is how debugging works. This is how you make sure that the solution is what you intend it to be. But the notebook you submit should not have 20 pages of printouts, right? Not all your scraping please in there. Because when you first render the notebook, it's not collapsing it, right? So the TFs actually have to scroll through all of that. I think as a summary, try to make grading, be nice to your TF, right? Try to make grading as easy and smooth for them as possible. Don't let your TF get annoyed. So please keep that in mind. Try to have your notebook executed when you submit, but do get rid of pages after pages of test printouts. So then just a recap to start where Hans-Peter left off last time. So he talked about k-nearest neighbor classification and about PCA and dimensionality reduction. That was last lecture. So you learned about this classifier here, right? We have all our training data. We have 2 classes. We have the blue squares and the red triangles. And then a new data point comes in. And in order to classify that, we take the k here. And in this case here, for the inner circle, k is 3. So we query the 3 closest data points in our training data and do a majority vote. So the 3 closest neighbors are 2 red triangles and 1 blue square. So the new data point is going to get classified as a red triangle. Really easy conceptually, incredibly fast to train because you don't need to do anything. Drawback is you have to keep all your data. Right? So you have to have a big database where all your training data is stored. And for each query, for each prediction that you want to do, you need to go through all your data points to find the k-nearest neighbors. So the prediction is really slow. And today we want to address this problem. So there should be classifiers out there that can kind of have knowledge about this decision boundary. Right? That's what it's all about. If you know the decision boundary, you don't need to store all your training data. So today we're going to first start to talk about separating hyperplanes. What do I mean by that? So here again, we said x are our data points, and then y are the labels. Right? So if we do image classification, the x is our image, showing cats and dogs. And then y is a label that tells is that a cat or a dog. Now for k-nearest neighbors, we didn't specify what the label should be. For the rest of this lecture, I'm going to assume that one label is +1 and one label is -1. And when I talk about the positive class, I mean the one labeled with +1, right? There are other classifiers where you have to do 0, 1. So this is actually worth checking out when you use a library. But with support vector machines, this makes the math really nice and easy. So I assume basically every library out there will use these labels, at least internally. So we have our data points, blue ones and orange, yellow ones. And we have the labels. Let's say the yellow ones are +1s and the blue ones are -1s. So now this is the separating hyperplane. Hyperplane, because you see it's just a straight line. I don't have the variability here. I don't have an S shape or something. I'm restricted to a hyperplane. But I could go to higher dimensions than just 2, so it's not just a line. So how do I specify this hyperplane? What are the parameters? So there is this weight vector W. So W defines the orientation of my hyperplane. So you can already see this is going to be one of our goals, to estimate that W. Because this is perpendicular to the hyperplane, so it's the orthogonal vector. So by changing W, I change the orientation of this plane. So now just very basic linear algebra. So if I have a data point x and my weight vector W, and I just do the dot product between the two. So the data points x for which this is true. Wow, whoops. What happened? The data point x for which this is true, right? They are perpendicular. Why is this happening? They are perpendicular to W, right? So we all have that in high school. Just keep that in mind. So now if I actually draw this in a coordinate system, and these are now just two-dimensional data points. So my data point x has 2 dimensions, so 2 features that I extracted. I'm calling these x1 and x2. So everything is living in this 2D plane. And now, because I only have W, my hyperplane is bound to go through the origin of my coordinate system, right? So now I don't want to be restricted like that. So we need a bias 2 to shift it around. So those are the 2 things I need to know my separating hyperplane. I need the weights W, and I need that bias. The weights to change the orientation, and the bias to shift my hyperplane around. And that means now if I have 2 classes, you can just imagine I can initialize those randomly and then optimize them to kind of wiggle it in between the 2 classes. That is going to be our goal. So now we want to separate the 2. And once we have that, prediction is really, really easy. Because all I need to do is take a new data point x and evaluate this equation. And that's really easy to do, right? It's just W transpose times x and add the bias. And then you just look at the sign of this result. So if it's greater than 0, so on this side of the hyperplane, we said if it's equal to 0, it's actually on the hyperplane. And if it's smaller than 0, then it's in the negative class. So the moment I have my parameters, I can forget about all my training data. So really efficient, right? So I can, not like in KNN, I can let go of all the training data. I only need to store these very few parameters. And on top of that, I even gained that my prediction just got very, very fast. But I paid for that big time because we're restricted to a line now, right? KNN is more flexible, right, and can do more nonlinear stuff. And this, at the moment, is just a line. So we are going to try and keep all the positive things about this without having to pay all the negative costs of KNN. So I'll first talk about the Perceptron. So this is the equation we just talked about. It's a separating hyperplane. all I'm doing now is I take this equation and draw you a diagram how to compute it here. This is my vector x, right? So these are the single x now is three-dimensional, 3 different features that describe x. So I have x1, x2, x3. And my weight vector w here is also just split into its single components. So just computing the dot product here is x1 times w1, x times w2, blah, 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 sum them up. And this bias here is here. So what we do is we augment our vector x and just add a constant dimension that we set to -1 in this case. And then we can, because then we can simplify the math and just have this in here. So this depends on your library. Some do this trick, some don't. So you have to look how you specify the parameters. So, but you see here, all this diagram here does is compute this equation. Here's my dot product, right? Sum them up. And then we need to decide for classification, if we actually want the label out, we need to decide whether this is greater than 0 or smaller than 0, and we actually have our classification. Now, people were really, really excited about this when it came out. Why? Because this is a mathematical description of a neuron. So you have a cell body, which is here. You have a dendritic tree, which are all these little guys here. You have the axon carrying the action potential and carrying the signal to the other neurons, and this is just our threshold, do we fire or not. So I can see this as a simple but mathematical model of a neuron. So when this came out in 1957 by Frank Rosenblatt, people were really, really excited. And this is a quote from the New York Times. And so he built this perceptron in actual hardware. And the New York Times said the embryo of an electronic computer that the Navy expects will be able to walk, talk, see, write, reproduce itself, and be conscious of its existence. So as before in history, they thought, we have found the model of the brain, right? That's what they were after. Unfortunately, oh no, wait, I found this really, really cool video, which I think is really cool, which I wanted to show you.
In the 1950s and 60s, scientists built a few working perceptrons.
That was too fast now. So I just found this on YouTube, and this is showing a very old TV clip of the perceptron that he built. So you're going to see this big, big cupboard-like thing behind him is implementing this perceptron, this small math model. In fairness, I think those are multiple ones connected with each other, but still, it's most probably not very big for today's standards.
In the 1950s and 60s, scientists built a few working perceptrons, as these artificial brains were called. He's using it to explore the mysterious problem of how the brain learns. This perceptron is being trained to recognize the difference between males and females. It is something that all of us can do easily, but few of us can explain how. To get a computer to do this would involve working out many complex rules about faces and writing a computer program. But this perceptron was simply given lots and lots of examples, including some with unusual hairstyles.
But when it comes to a beetle, the computer looks at facial features and hair outline and takes longer to learn what is told by Dr. Taylor. And Cruikshank's wing also causes a little heart searching.
After training on lots of examples, it's given new faces it has never seen and is able to successfully distinguish male from female. It has learned. While promising, this approach to machine intelligence virtually died out.
So that last sentence is very important to keep in mind. And it's making people laugh today, because this model, if I would have given this lecture 10, 15 years ago, I would have totally agreed with that sentence, because this part of research really did go in a very low. Now, these perceptrons are the basic unit of deep learning. That's what all the artificial neural networks intrinsically more or less are about. So this came out in 1957. This is why I always smile when people say deep learning is so new. No, it's not. It's been around there already. That cupboard thing there, there was an artificial neural network. That was deep learning. It was just on a scale, I mean, that poor guy, right, with his switches. What was that? That was the training. There wasn't even classification. They were training like that. Like taking each single picture, putting it under there, and then saying, did you see it was right or wrong? Man, woman. So he was saying, giving the computer the computer feedback, whether it did the classification right or wrong. So whether it should update the weights to get the classification right? Wiggle that separating hyperplane in between the classes. By the way, I asked Jan LeCun once how many training samples he would consider sufficient to actually think about training an artificial neural network, and he said he wouldn't start under 60,000. So that poor guy there with all the with all the pictures. Okay, so that about the historic context. So this came out, and everybody was very excited. And then because of the limitations of the hardware, and there were also some theory limitations pointed out, that last sentence, that it virtually died out, was true. There was no funding anymore. Only very few people actually cared about the concept. And until its revival now. But it's such a fundamental concept that you've basically already seen it before. So I said this perceptron has the step function, more or less. This goes from 0 to 1. I said ours goes from -1 to 1, but the concept is the same, right? We just look, is it smaller than 0 or larger than 0? And depending on that, we make our decision, which class to pick. Now, if I, instead of that step function, put a sigmoid there, right, which is kind of a continuous approximation of the step function, you actually have seen this before in this lecture, but very briefly. Does anybody remember or already know what I'm talking about? Yes, that is logistic regression. Joe had that on the slides earlier when you talked about regression and logistic regression. And they were actually invented, I think, 1 year apart from each other. They were published. So it was a very fundamental thing, and it keeps living on. I think part of the problem is that the statisticians and the machine learning guys didn't really talk to each other in those days. But so this concept is very popular and very useful and very good to understand fully and to know, because you're going to see that a lot of it comes back to it, like a lot of the things you learn in machine learning. So here's part of the reason why funding died. Right? There's Minsky, and the interesting part is Minsky and Rosenblatt actually went to high school together, and they have been known for very loud discussions on conferences, giving very, very hard disputes. And Minsky published a book called Perceptrons. And in this book, he pointed out weaknesses of those networks. And there's debate whether or not this book was part of the reason why the funding died. There were also other reasons, but this was widely accepted as pointing out really why there shouldn't be research anymore there. So, and unfortunately, Rosenblatt actually died very shortly after this was published. So he never got to see his method actually coming back to fame and all the people being excited about it. So some say this book pointed out the XOR problem. By now I actually I still haven't read the book. So if you do, please come to me and discuss it with me. Some say it was the XOR problem that broke the neck of the perceptrons. That's not true. People, even in the 50s, knew of this limitation. They also knew how to fix it. But it is a limitation of just a single separating hyperplane. So this is the XOR function. It just says, here we have 0, 1, and 1, 0 are 1, and 0, 0, and 1, 1 are 0. So I can't separate that with a separating hyperplane. Right? It's 2D. I only have a straight line. Whatever you're trying to do, just try it in your head. You cannot do a single line here and separate the two classes. Now that seems like a really fundamental limitation because XOR is such a basic function and we can't model it at the moment. So here's the very simple solution. We just add an additional dimension, and now we need a trick, and if we do the trick right, we actually make the problem separable. And now I can use a plane to separate the 2 points. So if I find a trick to lift the right points of the right class up, I can have my problem that was not linearly separable in 2D have separable in 3D, just by going to a higher dimension. Now that is really, Chris? Yes?
I'm just curious, is this sort of like the opposite of PCA, where you want to add dimensions to make things more separable?
So PCA does not make things more separable necessarily, right? So you normally have better separability in higher dimensions, but there's a problem with that. And why would I, even if classes are better separable in higher dimensions, still want to do PCA? Can you think about it? Can somebody else think about it?
Is it like an overfitting problem?
Yes, it's an overfitting problem. It's the curse of dimensionality, right? If I add more dimensions, I have these additional degrees of freedom, and my points are kind of spread out more, right? So I'm running into more problems. So normally, what you hope to do with PCA is get rid of the noisy dimensions and find the lower dimensional representation that still separates the classes. So basically, what you're trying to do is still do this kind of thing, like try to be in a higher dimensional space, but not so much, like I could do this in 4D and I wouldn't gain anything, right? I could add a fourth, a fifth, a sixth dimension without any information. And that even can hurt classification. So what PCA is trying to do, or what you're trying to do when choosing how many components to use from PCA, is find the number of components that give you a dimension that is so high that you have your points nicely separable, but so low that you don't run into problems with high dimensional spaces. That's the idea behind both. So part of this trick to take your points and just for the sake of making them separable, going to the higher dimensional space is part of what makes support vector machines so popular. And so now we actually made all the historical way to the support vector machines. So they've been used really, really widely, and some people say it's the best off-the-shelf classifier out there. I agree with some of the best shallow classifiers. I don't agree so much with the off-the-shelf, because you're going to see you actually have to tune some parameters to get SVMs to really perform well. So this higher dimensional part is one trick. The other one is SVMs do maximum margin classification. What does that mean? So here we have, again, our two classes. And here are two separating hyperplanes. For the perceptron, those are equally valid. The perceptron is happy because they both do not do any mistakes in the training data that we see here, right? They're all correctly classified. Now, who of you would prefer the one to your left? Who would prefer the one to the right? Yeah. So the left got the majority vote. I also would vote for that one, because this is really close to these points. So if you get a new yellowish data point, and just because of more variance, it's just slightly more to the left from this guy, this already makes a mistake, right? It's gonna generalize not as good as the other one. And this is what we're ultimately always looking for, generalization to new data sets. So, and this is how they formulate this. This is the margin around my separating hyperplane. And maximum margin means support vector machines try to make this margin, so the distance to the closest data points, as wide as possible. That's max margin classification. And it's called support vector machines because these then are the support vectors. The support vectors are the guys who define your separating hyperplane and your max margin because they're closest. So you can see, once I know these, I could in principle forget about all the rest there. Right? These are my support vectors. If I would have only those two, I would, not entirely, but basically get nearly the same result as if I have all my training data. So that could lead some people to say, well, I only need 2 points to train a support vector machine. Why do you still want a good amount of training samples to train your support vector machine, even it only cares about those that are close to the separating hyperplane? Yes?
There may be the rare points that are closer to the boundary.
They are the rare points that are close to the boundary. Yes. Like often when we have, okay, I'm kind of making this Gaussian assumption here, right? So these are further away kind of from the mean of this data point cloud, right? So they're the ones you're going to see more rarely. But they're also the ones that define your separating hyperplane. So the reason you want to collect all that data is to be hopefully lucky and get the right support vectors in. So this is then our maximum margin classification now. We have our separating hyperplane, and I'm going to just give you an intuition about the math. I'm only going to do the very simple part that you all should be able to understand. And just to give you an idea, because my ultimate goal is that when you see the scikit-learn function, you're going to see that there are parameters in there. And they don't have very speaking names. They're called C and they're called gamma. And I want you guys to know what C and gamma are about. This is my goal after this lecture, that you can go and understand the scikit-learn function. It's not so much about being able to prove anything here. So this is my separating hyperplane, and this is the maximum margin. And now if we look at a point that is directly on that margin, and we project it down to W, and we call that x bottom, then gamma here is just the distance. That is the width of that maximum margin. Okay, so this is my definition. So what do I know now? I know that this is x bottom. I know if I want to get from xi here and do this projection down, what I need to do is, this direction here is given by W, right? It's just the opposite direction. But W can have any length. So we're going to normalize it to length 1. And then I can use gamma to know how many steps of W I have to take to actually get to x bottom. That should hopefully make sense. Right? All I'm doing here is I take that point xi, I normalize the W to 1, and I do gamma steps of W down, and that gets me to x bottom. Why do I care about x bottom? Because I know that this equation here holds for x bottom. I know that this lies on the separating hyperplane. So I have these two equations now. That's all there is. This describes basically how to get x bottom, and this says for x bottom this holds, because it's on the separating hyperplane. If you understood that, you're done. That was the worst part about this lecture. So now we can just do some algebra magic and reformulate this and try to compute gamma, because this is what we care about later on, right? We said maximum margin classification. So if we want to find that SVM separating hyperplane, we want to find those W's that W and beta that make gamma as wide as possible, right? Gamma is the width of my margin. So, and I put Y here because remember, this is why we made them +1 and -1. Because now this label here defines whether my X is on the positive side or on the negative side. And this tells me whether I need to invert W to go down or I just use W and go up. So this is just why this Y is in here. And this is why it's so neat to have the labels +1 and -1 because it makes the math easy. So this is just what we had before, repetition. And then this is the whole, just written for your convenience, this is the whole problem we need to solve. And it's non-convex, but normally you don't have to bother about this because the software really does that for you. Would not expect you to write your own optimizer for a support vector machine. So let's just think more about the concept. So we've seen the separating hyperplane. We know about the support vectors. Why is this odd? When I first heard about the support vector machine, I was like, that's crazy. This is not what machine learning should be like. I really was not very happy. Because if you think about it, we said it's the rare data points it cares about. So what would those samples look like? Think about our apples and oranges, right? Let's say these are the oranges and these are the apples. Think about the color feature that we had. Those support vectors, what do they look like? Yes?
So they'd be orange looking apples?
Yes! That's so weird, isn't it? It's the oranges that almost look like apples. And it's the apples that almost look like oranges. Like when I teach my daughter, who's 2 years old, like this is an apple, this is an orange, I try not to show her the orange apple. I go for the apple that looks the most like an apple I could think of, right? And this support vector machine doesn't care about the ideal apple at all. They would be perfectly happy only seeing the borderline cases. This is what we're looking for with the support vector machine. It doesn't care about the very nicely shaped green apple. It wants the most orange one that still is an apple. It does make sense if you think about mathematically, but it was not what I envisioned machine learning to be like. Yes?
So what if you're missing data? So something's misclassified. So one orange is classified as an orange. Would that be really problematic?
Yes! This is going to come up right now. The question was, what about things that maybe are mislabeled or outliers in your data? This is exactly what I'm going to talk about now. So there are two things with this. So here, I just added one single data point. These two problems are the same, and normally I'm showing a really cool Java applet at this place in the lecture, and I noticed yesterday they took it down. So if anybody of you knows a really cool Java applet where you can like draw points and actually have the decision boundary shown, please tell me about it. Or if you want to write one, then also please tell me about it. So for now, we have to live with the pictures. V3. But is it interactive? With like? Ah, cool, I want to see that one. Because I was yesterday like, I should write one, but then I was like, not tonight. So, here's the concept. So this is more, maybe not the totally optimal solution. It was more by eye. But the concept is the same. So this is the same problem on the left side, on the right side. It's the exact same data points. I just added one more orange guy here. You can see it changed everything. Because it's really listening to the support vectors. And what I did there was, if I add a data point here, it has nearly no effect, right? But if I add a data point here, it changes my whole hyperplane. Now we said those are the rare cases, but those are exactly also the cases that might be mislabeled. Maybe this was actually meant to be a blue guy. Maybe that is an outlier. And I just changed my whole decision boundary because of it. That doesn't seem so clever. So let's do something about it. And this is even worse here. So here we have clear, maybe they are mislabeled, so this here is clearly in the wrong data cloud. Right? So we do not want a perfect classification on our training data here. So what we do is we tell the support vector machine, you can cut yourself some slack. These are slack variables. You see here what I do is I take the outliers and I measure the distance to the margin they should actually lie the opposite side on. Those are the slack variables. And you don't have to care about all of this. All I want you to, I hope because we went through this before, you're not scared of this part. The only part new is this part, and that's also the only part you care about, because there is your C. This is one of the parameters scikit-learn is going to ask you about. So what you can see is, in our optimization problem now, we have the sum over all the slack variables. So if I make C really, really large, it's going to care a lot about making the slack variables as small as possible, right? We're minimizing here. So if C is large, you're not allowed a lot of slack. So we basically get the solution we had all the time before in all the slides. Now if I reduce C, right, make it smaller, I actually say, okay, it's not that important in the sum here. You can see it's having some influence down here, and this is basically allowing the SVM to misclassify things. So if I make C smaller, then this is okay. So this is just what you need to care about, because it's going to ask you for that C. So now with the slack, I should hopefully get nearly the same solution. So now this point here does not change the whole decision boundary, because that slack variable accounts for it if I made C small enough. That make sense? So that's where it comes from. Here's an actual example. So here's a decision boundary defined by the support vectors that are all very close. And you see it's not making mistakes, but the margin is also not very wide either. And now, if we allow some slack, so C here is smaller, this was C basically infinity, so some very, very large value. So now we do the soft margin, which means C is smaller. So now it's actually finding a maybe more robust hyperplane here at the cost of misclassifying a point in the training set. And it can do that because it has the slack variables. Does that make sense? So we have the slack variables, we have the separating hyperplanes, and the maximum margin. That's already very neat, but we didn't solve that XOR problem yet. Right? And I promised you that the SVMs can somehow deal with that and use this higher dimensional space. So let's talk about that part. These are points, basically just in one dimension. And you can again see it's the same problem as in XOR. I can't find a line there that can separate them. Now what I'm going to do is I'm going to just take the square. I just added an additional dimension. And all I'm doing is before I only had x, and now I'm having the point x and x squared. And voila! I can have my separating hyperplane. Now, did I add any information here to the problem to actually make it separable? I see some shaking heads. No, I didn't. It's the same x. I didn't measure anything in addition. I didn't go out and put a laser scanner on my self-driving car. I just used the data I had. And I only added another dimension to my problem, making it the square of the coordinate I already knew about. So here you can see the same concept. because this actually allows the support vector machine to have nonlinear decision surfaces. So here's this cartoon style illustration of it. So I have 2 point clouds here that also are not linearly separable in 2D, but I blow it up to 3D and I find the separating hyperplane. And if you project that down again, you basically get this decision boundary here. And I found an even better video showing this. I really like this visualization. So here are blue points inside and red points outside. And what he does now is he shows you that parabola in 3D. So it's just what I just did in 2D and shown in 3D. So now we have the red guys here and the blue guys down there at the bottom, and the separating hyperplane comes in. And when you project that back down to the 2D plane to look at it, what you see is what we actually got is this circle-shaped decision boundary. So by using this trick, I can get nonlinear decision boundaries even though the math I'm doing is just linear. Yes?
Would you ever have to go up another, I guess, dimension? So in this case, we can only one, 2, 2, 2, will you ever have to go up to 4D, for example?
So the question was, to how many dimensions would you go up, right? Like what is generally done? The really cool answer is you can go to infinite number of dimensions.
So you could like go up a dimension, you still need to go up yet another dimension.
Okay, yes. So this is one of the parameters you have to tune. So the question is more, how do you know how many dimensions you should actually choose? So this is why I'm saying I would not call a support vector machine off-the-shelf classifier, because these are the things you still need to care about. You need to do cross-validation to come up with the number of dimensions you want to expand to, in a sense. So because what you care about, that number of dimensions is basically a parameter of your kernel. So what we're going to talk about now is how to do this trick with the higher dimensions math-wise in a way that is really, really clever and is going to save us a lot of computation. So I have this function phi here, and remember before I had just my x, and I did this parabola thing. So I took x and x squared. This is a quadratic expansion here, so I now have a 2-dimensional point, x1, x2, and I basically do the same thing. I have to the exponent of 0, right, and then to the power of 1, x1, x2, power of 2, x1 squared, x2 squared, and the product of the two. So that is a quadratic expansion of a 2-dimensional point. So now we said we might want to go to higher dimensions, higher than 2. That costs us. That is not going to be that easy. So what we need to do is compute all that stuff here if we want to have the dot product of the two. So because we want to operate in this higher dimensional feature space, we need the dot product between the 2 points. And now we need to take the dot product of the points with all these dimensions. So we're paying for this expansion. We're paying for getting to the higher dimensions. And at the moment, we're paying in computational cost. That is not what I wanted. And that's also not the reason people are so excited about this. The reason is you don't have to do this. You actually can compute the dot product in that high dimensional space without ever actually computing the point in the high dimensional space. That's as cool, I think, as math can get. So here, normally if you would compute that, I would ask you to write a program that does that. Naively, you would go and say, okay, I take x, I compute phi of x. I take z, I compute phi of z, and then I compute the dot product of the two. And what this kernel trick says, you don't ever have to compute phi of x to get the result of this dot product. You can just use this formula down here. And you see there's only x and z in here. There's no phi ever. And that is the kernel trick. And there is not just, so this is a polynomial kernel, and that doesn't only hold for s equals 2, you can go up to higher dimensions. So that is your parameter. If you have a polynomial kernel, you need to tune that s there. I'm actually not sure, is that called s or d for degree in scikit-learn? Rahul, do you know the polynomial kernel, what the parameter is called? For the RBF, the corresponding thing is called gamma. So, but if you use a polynomial kernel, you need to tune the degree of the polynomial. And that gives you more degrees of freedom, right? If s is higher, you go to higher dimensions, you basically have more wiggle room. So, and there is this other kernel, radial basis function, RBF kernel, that is very popular for SVMs. And this guy can be shown to actually go up to an infinite number of dimensions. And we can only do that because we never need the actual representation of that point in its infinite dimensional space. We only care about the dot product of the two. So, and here you see then the gamma that you need to tune for the support vector machine. And I'm going to have an illustration of the influence of gamma later. So, but first, what is this actual excitement? I mean, I'm excited because I like the math, and it's like, I have this high-dimensional feature space. I don't actually need to compute it. It's like free lunch, right? It feels like free lunch. So I'm not going to do all the math here. If you want, I have the link later on the slide. Andrew Ng, I think, does a really good job of explaining the math. And I actually, on purpose, followed his description. So you get a head start from my slide if you want to read his stuff. But there is a dual representation, right? This is you have seen before. That is our optimization problem for the SVM. There's something called a dual representation that has Lagrange multipliers in it. And don't worry about any of that, but look at this. There's our dot product. So these are my points xi and xj in my training data. And nowhere in this whole formulation is an xi or an xj by itself. That's the really important part here. There is only the dot product of the two. And I can get the dot product of the two without computing all the higher dimensions by using the kernel. That's what the excitement is about. I just showed you that you can compute your whole SVM in the high-dimensional feature space without having to pay the actual computational cost of that. And then in terms of prediction, when you do the prediction, it's the same thing. You need the dot product of your new data point with, and now the cool answer is not your entire training set, as we had for KNNs, but with only the support vectors, because those are the ones that define your decision boundary. So here's the link to the notes that are partly used. He also has videos on YouTube. Also the machine learning, not sure how much 181 actually does about it, but I would expect it to do more of the math. So if you actually want to go through all the Lagrange multipliers and the Karish-Kuntaka conditions, that's the place to go to. So just to summarize, we have the kernel trick for SVMs. We can go to arbitrary many dimensions with very little computational cost. And then, in addition, the SVMs have this maximum margin. And that actually helps to fight the curse of dimensions, right? The curse of dimensionality. Because we're trying to incorporate this to get the boundary in between with the maximum margin. That means that it generalizes fairly well, even if you have kind of sparse distribution of points. So that maximum margin helps with the higher dimensional space, which again helps with the kernel trick, which helps us with nonlinear classification. So it all goes together very neatly. Now here's an example that you actually all know how to do by now. So this is face recognition, and you should be able at this point in the course to go through this Python program line by line, Or even if you don't look at it, you basically can do it yourself by now. Because all they did was they took these faces, these images, this data set is called Faces in the Wild. You can download it. It's one of the scikit-learn example data sets. And what they do is they take PCA, which you learned, and then they take an SVM with the PCA components as features. And they get fairly good predictions. I mean, here, there are a lot of things here that got detected right. I actually think I would have made some mistakes here. So that's what they did. They load the image data. They put, then, because we're all good machine learning computer scientists, we put our test data aside, right? Hans-Peter talked about this, cross-validation. They extract eigenfaces, which we learned is nothing else than doing PCA on images. So you learned about that. Then they train an SVM, which you should be able to do after this lecture today. And then they evaluate the performance, which we're going to talk about also now. So, and this part here is basically what is inside your cross-validation, right? Extracting the eigenfaces, train the SVM, evaluate performance. You do that for all your folds. And you need to optimize what internally here? What are your parameters? You need to decide the number of components for your PCA. You need to decide which kernel to use for your SVM. And you need to decide on the parameters, the hyperparameters for the SVM, which if you use an RBF kernel is your gamma. If you use a polynomial kernel is the degree of the polynomial. Make sense? So in here, I wanted to have a use case of an SVM to show, that it works. And I thought this is another nice example. So this is a student who just used an SVM and very basic image processing to do sign language detection. So actually, can I stop that in between somewhere? So this is a cool example, I think, how you, with very little means, already can do things that impress some people with machine learning. Because the image processing here is very simplified. I think all he actually did was look for skin tone. And you can also recognize he's standing in front of a white background and he's wearing a black shirt. Those things make image processing much easier. So he's looking for skin tone, and then he knows that one is the face. It might even be that this position is kind of hard-coded, that he's looking for this big center blob. And then you're left with 1 second blob that must be the hand. And you already have a binary patch-like that looks hand-shaped-like, and then you can do simple shape descriptors. That is OpenCV. It's an open source image processing library that's based on C, but as far as I know, has a good Python wrapper. So these are things you can also look into if you're interested in image processing. And he's using an SVM here, and my suspicion is, unfortunately, he didn't list what he's really doing, but my suspicion is that he's actually listing most of his features here. So you can see it's the middle point here, so he has kind of an orientation of this blob here, right? And then you have a bounding box. And here in the circles, you have the fingers, which you can get by a skeletonization. So already very basic features can get you pretty far. It's also restricted. I doubt that this would work in a cluttered environment or if he actually would be moving. But it's nice projects that you can do to test your skills and get some programming exercise. Would I close this? So I said, let's talk about the influence of gamma. It's not that intuitive. It's this weird thing somewhere in this RBF kernel. So this is a figure I stole from the scikit-learn webpage. And it's very nice because it actually shows you how C and gamma interact with each other. Remember, C was the parameter for our slack variables. Right? So what you see here is, in this direction, we're changing C. We're making C larger. And in this direction, it's changing gamma. And you can see gamma here gets larger. So the larger gamma is, the more variability I have in my decision boundary. So here gamma was fairly small. It's 10 to the minus 1. And you have this very smooth decision boundary. And then when we increase gamma, you can also see these are exponential steps. That's very typical, and it's good advice if you have to tune these parameters. Go in exponential steps. So smooth decision boundary, and when we increase gamma, we allow more wiggle room for the hyperplane, right? It's higher, kind of the idea of higher dimensions, not really in this case. And then you can see the influence of C here is, so here C gets larger down here, which actually means less slack. Remember, we're minimizing over our slack variables. Large C means slack is bad. I'm penalizing slack. So, and as you can see it's really trying to make the best of its gamma, of its degrees of freedom that gamma gave it to fit to the training data. So this decision boundary here is a lot more wiggly than the one up there. Right? So if I allow less slack, my support vector machine is really trying to fit the data. And if I increase gamma, I give it more degrees of freedom to actually do so. And I can put that to a point that I have all my training data correctly classified and overfit. So you can, like in KNN with k equals 1, you can have these very small insulas that give you very nice training errors and not so nice generalization. So this is why you need to tune gamma and C. And you also see you want to tune them jointly. You really need to choose all the combinations. So tips and tricks for SVMs. Very, very, very important point. Please, if I wake you up at night and ask you, what do you need to do with your data if you want to train an SVM? You go like, scale it. Okay? So SVMs are not scale invariant. That means you really need to check your data and you need to normalize. That's the problem we had before. If one is in miles and the other one is in nanometers, in features, you might be in trouble. So you need to check whether the library you use already does the normalization for you. I would expect it to actually not do it. So then you need to care about it. So normalize mean and standard deviation. Or you can also try and map everything to 0-1 interval or -1 to 1. And also important there, you need to normalize the test set in the same way. And you're not allowed to use the test set to estimate the mean and the standard deviation for your training data. Right? Test set is really the situation. Whoever gave you the data is coming to you with a new data set that you haven't seen during training or something. The moment you need to load the data before training, the moment you need to load the test data before or during training, you're in trouble. You should be able to run your entire program without looking at the test data and only use the test data in the very end. So this is one thing to keep in mind. And then just general advice, if you don't know anything really about your data set, you're just like playing around, seeing what works, it's good advice to just try the RBF kernel and go in these exponential sequences for your cross-validation scheme. So these are just the things, they're like the black magic things that are being passed on from PhD student and student to student. And I found this very helpful. So this is a practical guide to support vector classification. If you think about using support vector machines in your final project or in your everyday research or in your hobby project, I would highly recommend reading this guide. So I'm actually gonna, so this is something you can think about. what are the main key differences between KNNs and SVMs? So with KNN, we needed to keep all the training data. We don't need to do that with the SVM. We only need to care about the support vectors. KNNs only have the K to tune. With support vector machines, we have already C and the parameter of our kernel and which kernel to choose in the first place. So everything is getting a bit more complicated, but we're getting these very nice max margin and kernel trick results and ideas to use. So I'm going to talk a bit about the parameter tuning because you need an evaluation metric for it, and this is what I want to talk about next. So this is just, again, a recap on what you need to tune for the SVM. So we already talked about cross-validation, and this is just a concept that is so important that I want to go over it again. So you have the error here, and this is whatever model you use in its degree of freedoms. And what you're going to see is when you start training, whatever classifier you're using, you start somewhere with a very high error, and then hopefully your model actually learns and the training error goes down. Now, if you allow more and more degrees of freedom to your model, you will almost always be able to get that training error to 0. At that point, the model might overfit, might be learning by heart. The way to realize that this is happening is to look at a testing or validation error. And what typically happens is the training error goes down. And this is when so basically here, I'm giving my support vector machine with a polynomial kernel more and more degrees of freedom, higher and higher and higher polynomials, right? To a point where it can make little insulas around every single data point and learn them by heart. So I have very low training error. I have a disaster if I want to generalize to new data here. So my testing error will go up. So the whole idea of cross-validation is to hopefully find the sweet spot. So if you think about K and N on this graph, where would that be for K equals 1? Would it be here near 0? Or would it be in the higher ranges of degree of freedom? Yes?
I think it'd be in the higher.
High, yes. You would be here, right? K and N with K equals 1 doesn't make any mistakes on the training error, on the training data. Classifies everything perfectly, because for each training point you have in your sample, it's itself the closest neighbor, right? So thinking about, try this. If you see these diagrams and about different classifiers, we're also going to talk about random forests and decision trees and things. These are the things that show you that you're actually grasping all the important concepts. If you can think about which parameter actually influences these degrees of freedom and where am I on the spectrum right now. These are very useful questions to ask. So one way to choose gamma, for example, is to do a grid search. Let's say this is cos, but let's make this C. Right? You have C and gamma, and this is nothing else than actually showing for each point here, for each combination of gamma and C, a score that was computed on a validation set. This is a grid search. This is basically what we've seen before, where I said this changes gamma, and in this direction changes C. But now we're also computing the score for each. We're not doing the visualization. We're just computing one number, and then we're visualizing this. Now, Hans-Peter is actually not jumping at me for using a rainbow scale. This is copied out of an actual paper. So I just use this as a reminder, don't do that. So, but to do this, not the visualization, the actual computing the grid search, we need to get the score somehow. We need to know which value to put in there. So let's talk about that. So error metrics. We're only talking about binary cases here. So I have a positive class, which was my +1 label, and I have a negative class, which just was my -1 label. I'm going to say true positive means that it actually is labeled as a 1, and my classifier also predicted it as a 1. So then I have a true positive. A true negative is it was labeled as a -1, and I also did predict it as a -1. So in the diagonal here, you have the places where we did everything right. And then the off diagonal here are our mistakes. And we make two types of mistakes. We can do false negatives. We were wrong in predicting it's negative because it's actually positive. And you can have false positives, which is just the other way around. So this is important to learn and know what it's referenced by, but it's also fairly intuitive. So, and now you can compute rates. And there's something called the true positive rate and the false positive rate. So the true positive rate is the true positives divided by true positives plus false negatives. So this is this row here. So I basically say everything that was labeled as true, how many of those did I actually get right? That's your true positive rates. The number of correct true positives that you identified divided by the whole number of positive examples in your training set or test set. That's your true positive rate. And the same for the false positive rate. You have your false positives divided by false positives plus true negatives. So again, it's everything that was labeled as the negative class, but now we're actually looking at those that we mistook as positive examples. And what people do then is they do an ROC curve. So we now plot the false positive rate against the true positive rate. Our goal is to have a small false positive rate and the very high true positive rate, right? We don't want to make so many mistakes, and we want to get a lot right. So this is where we want to be. This is where something ends up that just flips a coin. This is my 0.5 chance for either class line. So this is bad, right? This is close to my random line, my random classifier. So this is not where I want to be. I want to be up in the upper left corner. What about this guy? Good or bad? I heard some bad. I nod my head and I say but. Yes?
There is predictive power, but you have to flip around your...
Yes. This classifier actually does have predictive power, but you need to flip the labels. Right? So actually, if this happens, there most probably is a bug in your code. So I would go debugging. You can also say, hooray, and just flip the labels, and that would mirror it along this line. You actually aren't doing that bad. So this is just another ROC example. So that is what people typically do is you don't just do one point. You actually show a whole line varying over a parameter. For example, if I have a classifier that gives me the probability of a membrane in one of my electron microscopy images, I can vary that threshold and look at the classification mistakes I make. And you can see that you then get this characteristic. So this is describing more than just a single point. You can actually see the behavior of your classifier with respect to this parameter that you're thresholding. And I'm mostly showing this graph because there's something else here. So there are single numbers here, 0.5, 0.69, and 0.83. That is very useful if you do not, so mostly if you want read publications or if you write them, you want to show the whole curve. But if we do this grid search thing, we need one number, right? That curve is nice and gives a lot of insight, but we need one number. And one summary statistics that people do with ROC curves is the area under the curve. Like this whole thing has an area of 1. So if that number is a 1, I'm up here and I'm really happy, right? This is half of this, so it's 0.5. And this is just the area under the red curve and under the blue curve. So that is one possible summary statistic that you can use. So I believe you're actually going to do ROC curves in the homework. Is that correct? Yes. Because because they're very popular and widely used, and they come more from the statistics side. I personally work a lot with imbalanced data sets, and I like precision recall curves a bit more, but this is partly personal preference. So, but I also want to talk to you about the other option. So this is recall and precision. Recall is the true positives divided by true positives plus false negatives. We've seen this before. That was our true positive rate. Just a relabeling. But it's just a different name. And now we call it recall. But now this changed. Precision is the true positives divided by true positives plus false positives. Before, our false positive rate cared about this row. Now we're actually caring about this column. So we have recall, care about this. Precision, care about this. We are not looking at the true negatives with this measure at all. And that's the reason I like it. Because if you have an imbalanced data set, and I have this a lot, like there are only 10-15% membranes in the images I work with, and all the rest is background. So my positive class actually, also in the test set, is only 20% of the samples about. So if I would use an ROC curve, I will get pretty neat values, even if my classifier is not performing that well. Because I have a lot of true negatives. Even if I would flip a random coin, right? Because there is so many background, I'm having a fair chance of actually getting those right. I have an example about that later, but just to make this maybe a bit more intuitive, I think true positive rate and false positive rate is fairly easy to understand. With precision and recall, you have to think about it, maybe especially about the precision part a bit more. So recall is, if I pick a random positive example out of my testing data, what is the chance or the probability that my classifier would actually classify this as positive? Okay. And precision is, if I take a positive prediction example, so I ask the classifier, and it classifies all of it, and I take one of the samples that the classifier says belongs to the positive class, what's the probability that this is right, that it indeed is a positive example? Which means, let's talk about image processing, because it might be more intuitive. If I'm looking for membrane is my positive class, and I say everything is membrane, then with this definition I have complete recall. I find all the membranes that are in there. I have a very crappy precision, because just because I said it is a membrane does by no means, well, not by no means, but it doesn't mean that much, right? Because I say everything is a membrane. So this might be worth just sitting down and thinking a bit over. Like, think about these extreme cases. If I classify everything as +1 or everything as -1, what does that mean in terms of precision and recall? I was thinking to make this as an exercise, but we only have 10 minutes left. So again, it's the same idea as with the ROC curve. You can do a precision recall curve. Now, instead of wanting to be here, we actually want to be in the upper right corner. I find this more intuitive because you basically want both of these to be 1. You want precision and recall to be 1. With the ROC curve, you want your false positive rate to be 0 and your true positive rate to be 1. Here it's symmetric. You want to be in the upper right corner. You can think a bit about what this means for a classifier. It's good to show these whole curves, because it's not directly like, if I don't tell you anything about the underlying problem, you're going to have a hard time deciding which of those two is better. Because it really depends on your application. There are things where you care a lot about precision and not that much about recall, right? This classifier is better in that area. And this classifier doesn't give you that good precision, but it's fairly good with recall. So this depends on your application. Screening on an airport. We don't care that much about false positives. We just screen everybody. right? Because then we know our recall is going to be really good. It's like classifying everything as membrane. And the costs of having a false positive are not that high because people want to go to their airplane, so they maybe complain a bit, but in the end they go through the scanner, right? You can think about other scenarios, medical scenarios or things, and think about, do I want high precision or do I want high recall? What is the trade-off here? So this is a summary. This is the same classifier comparison. In an ROC curve, we want to be in the upper left corner, and in a precision recall curve, we want to be in the upper right corner. And you can see the ROC curve gives you the same result. It says this guy is a bit better in this area, and this guy here also is better here. So if you compare two classifiers, it actually doesn't matter which one you choose. They both have this power to tell you the evaluation of your classifier. I just personally feel that this is a bit cheating because this shows you you're actually not performing that well here. Right? There's a lot of room for improvement. Whether this gives me the feel, wow, it's doing really great. So Rahul is going to show you, I think, how to calibrate against this with ROC curves. There are ways to deal with this, but you have to think about it and adjust your ROC curve. But more about this in the lab homework. Both. So, and just like the area under the curve, there's also a summary number for precision recall curves, and that's the harmonic mean of just precision recall, so that's your F measure. Yeah, so we're nearly finished, just because so far we've only talked about binary classification, but a lot of the final projects don't just want to do binary. You want to classify multiple, you want to have more labels, right? You don't just want to do dog and cats, you also want to do rabbits and I don't know what. So how do you do that with a support vector machine when you only can do two classes? There are two possibilities you have. One is called one versus all. So you basically pick one class out and you put all the others together into one background class. And then you train the support vector machine blue against all, yellow against all, and red against all. So you actually train 3 support vector machines. So you need to train n classifiers for n classes, and then you take the classification with the largest margin, right? So this guy, if it's yellow, is going to be very nicely there. So you always take that one class that you go against all as the positive class, and then it has a large number if it's that classification. Does that make sense? So that is one. And the other option is 1 versus 1. So you take blue against yellow, yellow against red, and red against blue. So that lets you train n times n minus 1 divided by 2 classifiers, and then you can take the majority vote. So you let all your classifiers again predict, and just see which class was predicted the most. And this, of course, trains faster, right? Because you're leaving a lot of the points out. Before, I put all of them together into the background class. And now I'm only taking the 2 classes and do 1 versus 1. And then for multiple classes, this is your evaluation. You can look at a confusion matrix. And this is an image from scikit-learn. So if you compute a confusion matrix with scikit-learn, this is what your output is going to look like. So this is the popular iris data set. It's widely used. It's very little data points. It's nice to play around with, and it has these 3 classes. And this is the actual class of the flower, or I think the petals or something. And that is the predicted label from your classifier. And what you basically want is you want the diagonal to be very high. And you want this, the off diagonals, as low as possible. So the same idea as with the true positives before. So this says the true label is setosa and the predicted label is setosa for all these points, and we didn't do any mistakes here. Whereas this class here, that I'm not going to pronounce, is obviously confused with this class, right? This is why this cell here is not white. So this is the nice thing about confusion matrices. It does not just give you a number. It's not just accuracy. You're not just counting the number of samples you got right, but you can actually see where your problems are. So this is telling you you don't need to worry about discriminating these, but discriminating these two is a problem, so you might want to look into how to engineer better features or like tune your classifier to be better able to distinguish those. So that was my take for today. What we learned is perceptrons are really great. They were really great, and people thought maybe not so great, and nowadays it's all the hype. So, but they really just are more or less a separating hyperplane. If you stack them, they get nonlinear, but the basic concept in the little unit is a separating hyperplane, and that is actually also what an SVM in its true heart is, just a separating hyperplane. Kernels are really, really neat, and your evaluation metrics are important. That was it. Have fun, guys.